I'm Anand. I'm the chief scientist, one of the co-founders at LeadGenius. Let's jump right into it. I'm going to start out with a bit of a audacious claim. So I'm going to make the claim that within 10 years, the job of salespeople, as we know it today, is going to be replaced by artificial intelligence. And when I say replaced, I don't mean we're going to lay off all the salespeople in the world. There's still plenty for them to do. What I mean is that it's going to be radically transformed in the same way that automation and robotics have radically transformed manufacturing. Sales, as we know it, is going to be done by fewer people who are doing much more strategic, high-level work. And the reason I can make this claim with some confidence is I've seen some cool stuff that is happening at our company, some problems that are being solved by other companies that are like ours in our industry. And I'd like to dive into how these problems are being solved, talk a little bit about how we solve them, and hopefully share some interesting insights about what kind of data problems we're working on. Okay, so for those of us who aren't in sales, I'm going to go ahead and give us a quick run through of what salespeople actually do all day. And my apologies to people who are sales in the audience for hugely oversimplifying what's actually a very complex job. There's essentially three parts to sales as we think about it. Salespeople spend plenty of time thinking about which companies and people are out there that might want to buy something. So the old school idea of this is that salespeople have a giant paper Rolodex of hundreds of names. The best salespeople have thousands of names. They flip through it. You buy an expensive salesperson, and they can do this. The new school way is that you browse through online databases like LinkedIn, which have lots of information about who is working at various places, what these people do, and so on. Salespeople also spend a lot of their time analyzing those companies, those people, trying to figure out who is actually interested in buying what they're selling. So the old school ways, you might do some basic qualification based on your own best guesses. The new school ways, you might use tools like HubSpot or Infer or some of the new technologies that are out there to try and deduce some information before you get on the phone with somebody. And then, of course, the most conventional thing we think about for salespeople is they're actually spending time selling, engaging in a commercial conversation. The old school model, you're doing this on the phone. The new school way is you're doing a lot of this by email, a lot of electronic communication, followed up by some phone and some face-to-face, and lots more email communication. So sometimes salespeople will do all three of these steps in one. That's the cold calling model. You find people, you call them up, you say, hey, are you interested? No? Great, next person. The new school way, you're a little bit more crafty. You think about who you're talking to, and so on. Okay, so we can think about these as three different problems. Salespeople are spending time finding companies, sets of data, which is a search problem. Salespeople are analyzing those companies to figure out the intent, which we think about as the intent problem. And then salespeople are actually talking to people, which is the actual sales problem itself, the selling. So we're going to think about these in three different ways from a machine intelligence standpoint. We're going to talk about how we can build AI that finds companies, the search problem. Trying to figure out AI that can understand buying behavior, who's going to buy stuff just by looking at the data points. And we're going to try and figure out how to build AI that can actually talk to people, which is something like a Turing test, but happening over email. Okay, great. So let's go to each one of these problems in turn. We're going to phrase this in a bigger possible way. Let's ask the question of how we can figure out every single company in the world who might want to buy some company's product. And we'll start with a slightly more general problem of finding every company in the United States, and then we'll look at how to winnow that down to a subset of people who actually want to buy something. Okay? So we actually are solving this problem at LeadGenius. Here's how we do it. We crawl data from each one of 55 different sources. These are the first 55 we've looked at because they're particularly interesting, but of course there's no reason we won't grab more. We grab the public-facing parts of LinkedIn, the public-facing parts of Yelp, AngelList via its API, 50 different Secretary of State databases, which are hard to get information out of, SEC filings, and the IRS nonprofit database. Tools that were used here, Scrapey and Beautiful Soup. Scrapey to grab the information, Beautiful Soup to extract the information out of those pages. And some of these sites are really great to work with, like LinkedIn. This company directory is built to be crawled, so that is friendly. Some of these sites, like the Secretary of State's, are not so friendly and not so easy to get information out of. So after you grab these pages using something like Scrapey, you can deconstruct them to find all the interesting blobs of information on those pages. We can take those apart using Beautiful Soup. For example, here's Yelp's page where we've taken apart the document object model, pulled out all the different relevant pieces from the company name to the street address to the business website, plus a whole bunch of information about some interesting new things like, for example, you can see right up there, we're grabbing information about whether they accept credit cards or not. So there's lots of high-resolution information available in relatively public forums that we can extract and monitor at scale. Okay? Grabbing data from harder places like the Secretary of State databases is tricky. If you ever go to any of the Secretary of State databases in the United States, you will find that some of these websites are really nice to work with, and some of them are made with obscure and strange technologies that are hard to grab information from. So pulling data out of these sources requires some hacks, things like Seculi or Selenium that simulate browsers and let you click through to pull out information. It's a little tricky, but you can get this information out. Okay? So here's a little bit of a sense of the scale of this kind of problem. We did this with a compute cluster of virtual machines running in Windows Azure. We pulled about 7.5 million different looking pages for companies out of LinkedIn. Took about 40 compute days, but you can do that all in parallel for about $50 in virtual machine computing time. So pretty cheap. Pulled out about 200 gigs of data for a full text crawl. If we'd only stored the information we were really interested in, the data points, we could have kept that to be much smaller. Okay, but this is where you hit the first problem. There's actually far fewer than 7.5 million companies inside LinkedIn. Companies look like this, right? You can pull out a data point that's got an organization name, an email, a phone number, some address information, some country data, things like the revenue range, the domain, the organization size, et cetera. But you can see that one thing that happens a whole bunch, and this is one of our interfaces for looking over this data, you can find companies that are unrelated, that are not the same business, that have very, very similar names. So for example, this is a search we did on that crawl of data for a company name where we typed in ortho. And you see that we have lots and lots and lots of companies that we found that contain the term ortho that could be called ortho. Southern Ortho, Berman Ortho. You can even find companies that have the same name that are 100% character for character match, but are not the same business. Okay, so how do you figure this out? This problem gets more complex when you consider the fact that multiple companies might be referred to by different terms over time, even if they're the same entity or if they're related entities. So for example, Google, which is how we know this company that is now better referred to as Alphabet. And this is a problem that can be tricky to solve. So how do we solve this? So this is a problem known as entity resolution. And first I'll give you the fancy way that we solved this in the beginning. So we pulled a whole bunch of information about this company, about 30 different properties that we know about it, ranges from 10 on the low end all the way up to some of these guys we get 60 or 70 data points about them. You can create a mathematical vector, right? Just a straight combination of their name, their address, the revenue, industry, the founding year, technologies they use, anything we could pull off of that site about that company, right? And then we plot it in some mathematical feature space, right? So we convert each one of those things into a feature. So waving our hands a little bit, great. We can figure out the distance between each one of these companies, right? Which is basically a probabilistic estimate of how close those 2 points are in company property space. And the distance between those companies, the probability of them being the same. Okay? And then we just say those two companies are the same if the distance between any two of them or the probability is high enough or the distance is low enough. So that's a pretty fancy way to do it. You can see that we got out some interesting probabilities for different companies, and the probabilities range from 10% match to 1% match. So we have a range of possibilities, and we can apply some cutoff wherever we want to say that two companies in our database are the same company, or that these two companies are different companies. Okay, so the problem is this. That's super slow. You can do that reasonably quickly for couple of these data sets, but as soon as you're considering 54 different sources of data, many of which have redundant data, sometimes that have redundant data about themselves, you have a very, very slow process. So this takes about 7 days right now for us to totally deduplicate the entire set of data that we grabbed from those 54 sources. Not a great way for us to keep data up to date really quickly, especially given that that data is falling out of date probably faster than that 7 days allows. Okay, so here's a quiz, and for a small crew I can ask for ideas. Who can think of an easier way to solve this? The problem of if two companies in our data are the same. Sorry? Ask who uses it?
Ask your users, like get your users to say, do you think these companies are the same?
Yep, so that's a very easy way. You could surface this up to humans. So we looked at this approach. We have a crowd of about 500 people, which is our secret weapon behind the scenes. They're paid and they work for us. So we can use them as a compute resource as needed to resolve some of these questions. However, that only works if you know the probabilities of these things to be low enough that you only have a small number of duplicates. And it turns out that we had a high number of potential duplicates, companies that looked like they had relatively similar probabilities. So unfortunately, the cost of asking humans is a lot higher than the cost of asking a virtual machine. And so we have to reserve only for things that are truly obscure cases. Okay, any other ideas?
You can trace the history.
Yep, so that's another way you could do this. If you had enough information about the history of the points of the data companies, you could see how things diverge over time, and that's something we did introduce as a method. Well, so there's actually a third method that we've tried out, and it turned out to be a ridiculously simple and unexpectedly cheap way to normalize this entire data set. We looked at a very, very small subset of properties that were unlikely to change very often and that we could standardize with real ease. And it turned out that this method was good enough that we could normalize just about all of the data that we had in our database ridiculously well. So we actually went to the US Postal Service, which has a third-party API that you can use. And it's a very, very, very old-school government technology that lets you feed in an address and get out a standard normalized address. And that was enough for us to normalize over 95% of our data, which was surprisingly good. We just fed in all the random data formats that people typed in on these various pages for the addresses of companies. It came out as an address, and the address was standard no matter which person had typed it in, even with typos and different spellings of boulevard or suite. And then we could just do a string match. And that actually worked pretty well. Two companies were the same if and only if they had the same physical official address. Okay, so there's a complexity to this, which is that companies do move over time, and they also may have different chain locations if they're a franchise. But we can wax over those subtleties and just hint at the fact that if companies move, we can trace that information over a long-term basis. Okay, so that's the easy way to do entity resolution that we came up with. Okay, cool. So what did we find out? How many businesses are in the US? So there are actually 21,708,021 US businesses. The vast majority of those turn out to be very, very small companies just with one person. Basically mom and pop establishments, or maybe an individual plumber or accountant who is registered as a corporation somewhere or an LLC somewhere. There's about 6 million businesses in the US that have more than one person. Those are the interesting businesses for most of the sales use cases, unless you happen to be selling to plumbers or individual decorators or something. So each of these sites, Yelp has about 47 million establishments, but a lot of those are retail locations for different companies. So lots of those are the same company. LinkedIn only has about 2 million unique companies in the database, at least for the US. Crunchbase has about 650,000. AngelList has about 289,000. And a lot of the AngelList ones are sort of at the border of being companies and not. Okay, so some basic queries you can answer of interest on that data set. So which industries are the most common in the country? Do you guys have a sense of which industry has the most locations or most type of locations or distinct companies in the US? It's good location. Yeah, good answer. Retail companies in LinkedIn, however, are listed as one big company, not as distinct locations. So I didn't know the answer either, but it turned out it's construction. There's more distinct construction organizations in LinkedIn than anywhere else, followed by real estate, followed by IT. And that doesn't necessarily mean that there's more IT companies out there than healthcare or marketing agencies, but it does mean that there are more of those that advertise themselves in LinkedIn than anywhere else. So we can answer some more interesting questions about certain kinds of companies. This is one data point that I didn't expect. How many Fortune 500 companies have websites? The answer is 499. There's one that was tricky to find that didn't have a website. I'll let you guys come ask me afterwards, and I'll let you know how to look for it. I won't give you the answer yet. It's not LinkedIn. Okay, cool. So there's a bunch of bonus problems here, and I don't want to talk too much about how to solve these particular ones, but I will comment briefly on them because I think they're interesting and worth thinking about. So the first problem is the question of how long this information is still good after we grab it. So we did spend a little bit of money to grab that information. It wasn't a lot, but it was a little bit. And it's a little compute intensive to grab information from all these places, especially if we have to invoke humans to clean up any part of it, which we do to some extent. So it's a good question to ask, how long is that information trustworthy after you grab it? So the way we model this behind the scenes is with a decay function. Over time, we assume that the information slowly goes out of date. You can grab census information that actually tells you how likely it is that information will change in different industries, but of course, over time, it'd be great to back that up with our own observations of how often that information is changing, which I expect we'll be able to get as we start monitoring this data more and more often. The next question is how often it's best to grab this information. If it costs you $50 to crawl LinkedIn once, $50 to crawl Yelp once, you maybe don't want to do this every hour, maybe don't want to do it every day, you should do it every week, every month. So you can maximize the expectation that you're going to need to grab a piece of information that's fallen out of date with some sort of basic expectation maximization algorithm. And the last question is, I talked about those 54 sites, most of which have cleanly structured data schemas. There are some sites that we look at that don't have clean schemas, and this is a problem we're still working on, which is how you can figure out how, if you're watching a human being grab information from a website, you can deduce what the schema looks like for that site on the fly. For the other ones, we had to go through manually, hard code the schema. As the schema changes, there's lots of problems in getting that information out over time. So that's a bonus set of problems that we'll look forward to working on. Cool. Let's go on to something else. Let's talk a little bit about the intent problem, how you can build machine intelligence that will understand buying behavior. So the first thing I want to say is that, well, I'll give you the problem first. So assume we're a company that's come to LeadGenius. We want to figure out a set of companies who are going to buy from us in the future. And as training data or background data, we have a full set of companies who have bought something from us in the past. So typical model is somebody comes to us, says, here's our marketing database, here's our sales database, here's everyone who's bought something from us in the past. Who out of that big set of data that we just crawled out is going to buy from us in the future? Okay, so this is a really hard problem. It's so hard that I won't claim that we are solving it to completion, and I don't think anyone is going to solve it to completion, but I do think there's an interesting set of approaches that we are looking at and that some other companies are not yet looking at. So I'll tell you why I think this is hard. The first is that it's non-generalizable. If we build a model that can predict sales for one particular industry, the conditions that decide if that company is going to buy something are probably not the same in any other industry or in even any other product. The second is that this information is totally time dependent. If you want to buy a car, or if you're a company that needs to make a new IT purchase, that's going to change. That's going to be very specific for a moment in time, and it's not going to stay constant, except in maybe very special cases. So it's super hard to get this information in a way that is right for a given moment in time. So we can get approximate solutions, is the good news, and that's what we're going to try and talk about right now. So the general approach we're going to take, and this is the conventional approach that's followed not just by us, but by companies like Infer or 6sense that are also looking at this question, is machine learning. We have a whole bunch of companies. We've got mathematical representations of them as vectors based on our parameter space. All we need to do is try and make a solid classifier to separate which ones are going to buy from us and which ones aren't. Okay, so easier said than done. How much data do we need? Rule of thumb for a classifier like this to do any good, need about 10,000 samples. So if we happen to have a company that has 10,000 customers already, great. We can start to make some interesting algorithmic deductions. If not, okay, we'll need different approaches. Okay, so we train up a neural network. The approach is always the same, right? You train up a neural network or your favorite classification model of choice by showing it a whole bunch of examples from the customer's database of companies who have bought the products in the past, right? We have feature data on each one of those companies, so we match them up using our energy resolution system. We decide what the features are that are relevant. We learn a function that tries to separate these objects in space, right? You separate out some part of the data, you train it on the other part of the data, then you test how well that function did, you mix up your data, try again until you get something that looks like it's fitting, standard approach. And then for new objects, in principle, you're predicting which type of thing it is, right? You can decide if this thing is going to be a customer or a non-customer. Okay, so that's the idea in theory. In practice, much, much harder. And yeah, the way we talk about this is companies that match an ideal customer profile for a customer, or companies that don't match an ideal customer profile. And we can make a claim about whether they are or are not based on our classifier's output, but it's important to frame that as a recommendation and not a ground truth, because there's lots of hidden variables that we're not accounting for, as I mentioned earlier. Okay, so here's a better strategy for how you can improve this just a little bit using human beings, which I think is a way to try and improve this approach, even in the face of the fact that there's a whole bunch of limitations to what we're talking about. So rather than treating this as a hard classification, A or B, you can pull a probabilistic estimate, right? How close are we to that separation hyperplane to decide if this company is actually in market for a product or not? And if the probability is low, say it's below 80%, you can bump it up to a person, to a human being in our workforce, who can actually make a determination based on what they know about whether that company is a likely buyer or not. Potentially, they could even add a feature or tell you, hey, here's a feature that lets me make this decision better. And then after you make that call, you add that data to the training set to make the classifier smarter. So not an atypical active learning approach. This, in theory, boosts the likelihood of success to human levels, but it really depends now on that human and how good that human is in making the determination. And at least the way that we've set it up in our system, we try and have humans work on specific projects or campaigns for specific customers so that they have some fluency in a given domain. But I think this approach still leaves a lot of questions somewhat open. Really what we're doing is trying to filter down that gigantic set of companies into something that's more manageable. I don't think we're yet at the point where we can say definitively a company is going to buy or isn't going to buy. I think that's going to still take some years of work. Okay, so some other things that we're looking at and thinking about. One thing that's interesting that we suspect is going to be strongly correlated with buying behavior is watching behaviors of different companies or people at companies in our space. So for each one of the companies we've crawled, if we could get this information, it would be useful. We have talked about some ways that we can grab this information as part of our crawls. For example, if they've started hiring for a product, for a role that would use a company's product. For example, if you're hiring for a VP of sales, you're probably going to be willing to consider new sales technologies. If you're tweeting about a problem that's relevant to a given company, that is an extraordinarily strong indicator that you're probably interested in buying something around that. If you're looking at a website that sells that technology, assuming you can get that information, great, that's an indicator. Same thing for job positions that are relevant to that product. If you're opening up a job description on your company website for people who would use a given product, you are probably interested in that product. And then if somebody's replying positively to emails that are being sent, and I'll tell you a little more about how we can get that information in a minute. So all of those behavioral signals, most of them are public, some of them are not. For the ones that are public, we think adding that information in will let us boost the accuracy of these kinds of claims. The next part is, of course, stage. We haven't proven this out yet, but we have a hypothesis that companies will need to move through different stages in their life cycle over time, especially for startups going up to different rounds of funding and sizes. You can figure out where they are in a life cycle as a business and then match them against similar companies, what they've bought during those points in the life cycle. So that's the high-level idea. Okay, great. Let's talk about the last problem, and this one is one that I think is the most interesting out of the three, which is figuring out the last piece. How do you communicate with people automatically in the same way that a salesperson might, or the same way that a sales communicator might? And I call this the email Turing test. So the basic question looks like this. How do we write messages by email that are as good as those that are being sent by a human being? So how do we communicate in a salesperson's own voice? How do we write messages that look authentic? How do we write messages that actually look like they're being written by the person whose inbox they're being sent from? Not just from the recipient's perspective, maybe from the sender's perspective as well. So the context here around this problem, there are tools like Tout, Yesware, lots of email automation tools that try and send out lots of drip messaging at scale as part of lots of sales campaigns. These don't really send out messages that are necessarily effective in the sense that they don't necessarily sound authentic. And maybe you get messages like this a lot. I know I do, where it looks like it's been a canned message sent out to thousands of people, either for recruiting or for trying to pitch you something. you don't respond to those, you don't engage with those, you delete those. What we'd rather see is a model where people are actually engaging in effective, meaningful conversations over email that look like, or at least are the same quality and utility as somebody who is being written by a human being. So, this is actually a big problem. This has been around since the 40s, and it's hard. It's the Turing test, but happening over email. So it's fair to ask if this is even plausible. So I want to make the case that this sort of thing is plausible, that we actually can have really meaningful, effective communication over email that looks like a person. So there's a few examples from deep learning recently that say that this is becoming more and more possible. So there's a great example, Xiaomi, which is a product out of Microsoft in China, which was trained on real-world chatbot logs to produce really effective human-to-human chats, all via machine intelligence, general topics, so not really a lot of room for it to go wrong because it's a chatbot, but it seemed to be pretty compelling for a lot of use cases. And then, of course, customer support. There's a great example here from Google of an automated support interaction that looks extremely plausible, where the machines part is being done based on a deep learning system trained on lots and lots of historical chat logs. And you can see here that the conversation follows a natural thread. The communication is short and it's domain specific. But despite that fact, we seem to be moving towards a useful set of recommendations and a useful set of solutions. So I want you to look at the thread here and the flow of conversation to note how it's moving, right? There's general topics that are being discussed, but there's also a flow that's directed because this is a structured domain. So there are greetings, simple for a machine to handle. There are basic queries that are being used to narrow the domain of interest. There are basic questions that are being asked based on data that we know about the person. And then there's some statements that are being made that are simulated from chat logs or from historical trained data that seem to be resolving the issue or making recommendations that are useful. And you'll notice that it's not perfect, but it also doesn't need to be perfect, because for a chat interaction like this, to give people useful suggestions in a natural way is enough to advance the conversation. It's not necessarily a requirement that it is maybe a perfect level of communication. And in fact, if you've been on customer support chats with online agents, you may find that the level of communication is basically at this level. So I break this down into two parts. Communication, whether it's via chat in real life or via messages sent by email, takes two parts. It's us composing a message, right, thinking of what to say, and then understanding what somebody is saying back to us in response, and then looping on that process, making decisions on what to say next based on the history of conversation. So we'll look at each of these two problems in turn, okay? So for the problem of actually writing a message, we have a few secret weapons that maybe some people don't, but the data that we start with when we work on this problem is the following. We have an author, meaning a customer who comes to us and says, hey, you're going to send emails on my behalf. They give us their entire inbox of data. We integrate into their Gmail or their Outlook to get access to information, and a recipient who we know we're going to send to. We want to try and compose a message that's going to have the maximum likelihood of getting a positive response from that person, and hopefully that looks indistinguishable from an email that was sent by an author. So when somebody gives us over their inbox, we're going to try to figure out how to send a message that sounds like them, looks like messages they've sent in the past. So this is, again, the Turing test. The fact that we're restricting this to sales, which is a narrow domain, and email, should make it a little bit easier for us. Okay, so we have two secret weapons we can use. The first is that we can mine that inbox, obviously, to grab some training data if we want to, or at least look at some examples. The second is that we can choose to ask a human being from our crowd of trained folks for help in optimizing that message. Okay, great. So here's our overall strategy. The first is to craft a template, ideally by looking at examples of what that person has sent in the past. The second is to collect data at scale using crawling techniques or human beings to try and populate that message with sender-specific or recipient-specific content that will be useful in a conversation, and to change that content based on what we know about the recipient. Okay? So here's an example of how a message like this looks. And you can see some highlighted areas where we have identified things that will change based on what we have discussed about topics with that person. So For example, a client like this might have us write, we know each other through so-and-so, and I saw that you guys were doing activity blank, right? We're doing activity blank. In this case, was hiring for a given role. And then we make an offer of some kind, which is a more or less canned statement that addresses the specific problem that we think that person has. And then we go further and say, hey, we're doing this for somebody that you know in your network already. And then we reference some recent fact. So this is a pretty simple conditional set of information that we discovered about somebody that let us craft a message that actually proved to be pretty effective in practice. Okay, so taking this further, we really want to know whether messages that we produce are actually effective before we send them. Because if you send a message to somebody and it's not effective, you've just wasted somebody's time and made the world a worse place by sending a junk email. So you really want to figure this out. And we've been working a little bit on this problem recently to try and understand how likely somebody is to respond to a message before that message is sent, after that email has been written. So the things that we're looking at right now, length of the subject, length of the email itself. We've done some word analysis to look at the tone of that email. We've looked at the complexity of the word choices, the complexity of the subject line, whether that subject line contains variables or didn't contain variables. We looked at the word choice. And then the goal is to show this to the user and optimize based on that. So some early stuff that we've discovered. We found some obvious things about length. This is a basic regression model. The longer the email subject, the less likely it is someone's going to open that email. No surprise there. One surprise that we did find, looking at the subject line itself, if you include variables in your subject line, this is far less likely to make somebody want to open your email. And you may try this out as an experiment. Look at the emails that you've gotten in your personal life in your own inbox. See how many of them included some content that you could consider a variable that would be different from person who's sending you email to not. So the typical things that people included when we analyzed our data as variables inside emails were things like first name, comma, here is something you should look at. Nobody writes to you and puts your first name in the subject line of an email. So that's why it looks like variables are not having a predictive impact. So we recently put together a more sophisticated model. We were able to predict with about 75% likelihood, at least as well as a human being, whether a message would actually get a positive response or not. So we're on the right track. We're not there yet, 100%. Okay, so once you have this information, you can start doing some interesting things with it. This is some work we did in 2014, trying to use human beings to improve templates. These are human beings from our crowd of 500 people. You can see on the left this was actually just a blog post about visiting a conference where we wrote a really rough outline that wasn't very sophisticated. We hit a button, summoned a person from our human workforce. They went through and fleshed it out very quickly, and within 24 hours gave us back a pretty good looking, coherent blog post. So this is suggesting that once we find structural deficiencies in emails, we can try and correct them at scale on behalf of our users. Still future work for us to actually implement this, but I think it's pointing us in the right direction. And there's some papers on this you can take a look at if you're interested. Okay, cool. The last thing, the next part of this process is understanding responses. So after we've actually delivered a message to somebody, after we send somebody a message, we really want to know what they're saying back to us. Are they saying, yes, let's talk further? Are they saying, no, I don't want to talk to you? Are they saying, I have questions about this, this, and this? And so we looked at a structured subset of this. In the domain of sales, we don't need to necessarily understand the entire universe of everything somebody is asking us about. We just need to know, is somebody saying, hey, yes, I'm interested, or no, I'm really not interested, or are they saying, I'm not here right now, or I'm the wrong person to talk to, go talk to that person, which is a much simpler problem. So this is an example of a customer inbox in our product. You can see that we've flagged with different colors somebody who is replying positively, saying, yes, I'm interested. Somebody who's replying negatively, saying, no, I'm not interested. People who are saying, I don't want to talk to you, take me off this list. People who are saying, this is good, let's send it to somebody else inside the company, go talk to them. People who are saying, I'm not here right now, this is out of the office. So we're actually able to achieve pretty good classification, pretty close to 100%. How do we do it? Well, there's two approaches you can take. The hard way is sentiment analysis. There's a lot of literature about it. Good paper to start on this is the Twitter one, where you can grab a giant corpus of data from Twitter, which has been hand annotated for positive and negative sentiment. The basic approach is always the same. You got a bunch of words or symbols. You look at the words in combination. Some of them are positive, some of them are negative. And you can find correlations between positive themes, negative themes. You can look at more complex models like n-grams of that data to see which n-grams are positive and which n-grams are negative. And this works in general. It's kind of a slow approach in that you need a lot of data. And there's lots of places that this can go wrong. And at least for us, the thing that we're keen to avoid is the critical failure in a communication channel, where somebody says, no, I'm not interested, I don't want to talk to you, and you say, oh, well, let me tell you more, because that's places where you can tell that you're not talking to a human being, you're actually talking to a machine. And conversely, if somebody says, I'm really interested, and you write back and say, I'm really sorry to have bothered you, okay, you've also just cost that person a lot of money. So we actually took a different approach that got a much better result, and it's better than any of the sentiment analysis results that we looked at, including the stuff in literature, and we basically cheated. What's the easy way? Well, the easy way is human computation. You ask a person. And you can do this surprisingly quickly. This is a screenshot from our interface. You can see that we can grab information very, very quickly and just have a person click through lots and lots of these emails. If you're unsure about their reliability, you can ask a second person to give you a second level of quality control, which we do, and we have a sophisticated model that only asks people to review large amounts of this data to make sure that it was done right. Great. So, okay, the last thing you can do, once you're pretty good at classifying emails, is you can start to script entire conversation paths, which is pretty cool, because this is giving you the basis for, at least with a finite depth, some form of totally automated communication. And our goal, at least in this process, is to do the part of sales that is happening via email, not to do the part of sales that happens on the phone, because that's a little bit beyond us. So what we do right now is successfully classify these emails based on the type of information they've had. The next thing you can do immediately is start sending emails based on the response type, right? So if somebody says, I'm interested, you should come back with the natural next step, which is, oh, here's times that work for me. Or you should say, if somebody says, check back with me later, or let's talk to that other person, the conversational system should be able to say, okay, I'll go talk to that person, or I'm going to schedule a follow-up with you in a few months. And more or less, this system should happen without the intervention of a salesperson, since this is what people spend a lot of time doing, more or less automatically. Yeah, and then eventually you can script this out into an entire conversation, some of which have threads that will end in a positive response, meaning somebody's on the phone, some of which have threads that end in a negative interaction. And the nice thing here is that you can choose to use sentiment analysis to hone this process if you want to use human beings less, but it's actually pretty efficient to use human beings to just classify things, as long as the conversation threads and the different choices in the path are all defined in advance. So we have if you set out templates for each one of these situations. Okay, great. So we talked about 3 problems here. We talked about the search problem, how you can build AI that finds companies. We did that by crawling the web at scale. We talked about how to build AI that understands buying behavior. We did that with some basic classifiers and some humans. And then we talked about how to build AI that can talk to people. And we did that with a wide variety of technologies, but we used a lot of human beings too. So company search can be attacked by large-scale crawling, some human computation, paired with good entity resolution techniques and some data updates that track information over time. Buying intent, still super hard. You can do it with classifiers, but it's right now done better with human beings in the loop. And email communication is complex and has a lot of interesting sub-problems, but at least in the sales domain, it's pretty solvable. Great, so if you're interested in learning more about this, come talk to me. I think we'll do some Q&A right now. You can come talk to us as a company if you want. If you're looking for a job in data science, we are hiring. You can tweet at us on LeadGenius on Twitter at LeadGenius. You can write to me also directly. I love talking about this stuff, so happy to talk anytime. Great, that's it.